So let's get started on these and just go through them and make sure we remember all the little properties that you learned a long time ago. Let's see here. So recall that if you have some exponents and you're multiplying them and they have the same base, right, the same number, right, you're really counting how many you have total. So you just take however many you have here and you add it to however many you have here. So this would be x to the a plus b. Right. And likewise, if you're dividing, you're saying, well, how many you have on top with how many will cancel on the bottom. So you just subtract them because they're canceling out. So this would be x to the a minus b. Right. All familiar, these are all algebra 1. Then we have the power to a power. So you have how many groups of the base to that power do you have? So you just multiply those. Right. So those are the basics from algebra 1. And then algebra 2, maybe even just this class, you might have just learned about the fractional exponents, which of course were roots, right? So you know the 1/2 power is the square root. The 1/3 power is the cube root. So anytime you have a number on the bottom, that's like taking that root. Right? If it's 2, it's a square root. If it's 3, it's a cube root, and so on. And then we have the number on the top, which is just a regular exponent. So you just take, x to that whatever power it is. So really, I look at this as just taking the b away from the a and making it an nth root. And there's 2 ways of doing this. The first one is already there, which is you would actually take the variable to that power first and then find the root. But you could also do it the other way, which would be this. And sometimes this is even more common. You would do this and then afterwards raise it to that power. All right. Both of these will work. Whether the a is on the inside or the a is on the outside, it all works the same when we're just dealing with numbers. Okay, so either one. And we'll look at that when on a and a1 right here, we'll look at those differences. And then we got a few more. Remember that right here, biggest thing here is that negative exponents equal positive fractions. A negative exponent is a positive number. Okay? Negative exponent is a positive number. That's why in chemistry it says this, element or this, how many moles there are, and it's like 3.6 times 10 to the negative 23. Well, it's to the 10 to the negative 23. It doesn't mean it's a negative mass. It just means it's very, very small, subatomic, super tiny, but it's still a positive number. So realize that negative exponents are positive fractions, and we can rewrite them this way. It's 1 over, right, x to that power. And then lastly, anything to the 0 power is 1. That goes along the first 3 over here. That's just a basic rule. But these other 2 right here, we're going to practice a little bit more than the other ones. But we're going to use them all together several times in one problem, put it all together. Any one by themselves is not too bad, but we got to be fluent at using them, however many times we need to use it in one problem. Here's a little table. You probably recognize, a lot of these powers, maybe up to here. Let's see here. 2, yeah. These are very familiar. But then when you get to, maybe 125, do you know that 5 to the 3rd power is 125? Do you know 6 to the 3rd power is 216? It's just that you'll see these numbers coming up, and it's okay if you don't have it committed to memory at this second, but you also want to recognize these numbers, especially something like this. 2 to the 6th power is 64. These are just good things to recognize, even higher as you go if you do a lot of this stuff. But you can use this table on the homework today. Might be useful. So let's look at doing a few problems. I'm trying to get this. There we go. So simplify without calculator. So even though you could just put this in a calculator, you want to know how to do it without it. It's going to be a no calculator part of the test. They're going to have two parts, I believe. So one with, one without. So you want to know these rules, but you can always just check it using a calculator. So you can see there's quite a bit going on, and here's, as mentioned earlier, there's kind of two ways of looking at it right here. Right? We can take the root first and then to the exponent, or do the exponent first and then take the root. So you'll get the same answer either way, but you'll probably notice one is a little bit easier than the other. And this one, my opinion, would be this. Take the root first, right? And then raise it to the -2 power. Because you know the cube root of 8, right? You know that's 2 times 2 times 2, so it's not. It makes the number you're working with smaller when you do the root first, right? And then you can raise it to the second power, right? Or -2 power, which would be, of course, be 1 over 2 to the +2, which is 1/4. Now, if you did it the other way, just for argument's sake, if you did it the other way, you would have cube root of 8 to the -2, right? And then you'd have to find the cube root of 8 to the -2, which would be 1 over 64, right? And 4 times 4 times 4 is 64, so 1/4 times 1/4 times 1/4 is 1/64. So you get the same answer, but you can see probably this method is easier. Doing the root first and getting 2 and just raising that -2 is probably a little bit simpler to think about than, you know, what the cube root of 1 over 64 is. But they are indeed the same. So either way. Go ahead and try number 1. Just break it up the same way I did. You know, you can do it either way or both ways. You know, just try it out. Focus on just showing the work and being clear in your thinking. You know, is probably the most important thing here. And you'll notice that you don't necessarily, since it's a 2, it's implied when there is no number, it's automatically a square root, but if you wanted to put it there, it wouldn't be wrong. So square root of 16, of course, is 4. And then 4 to the 3rd power would be, go over here, you know, check the table, see what it is, if you don't already know, and we already did it here as well, 64. There we go. This is our first answer here as well, 1/4. All right, and then B and 2 are very similar, just using all the properties, simplifying. These are Algebra 1 problems, but just know that you probably want to do the multiplication of the power to the power first, and then do the adding, almost like an order of operation. When you're going to multiply exponents or add exponents, good to multiply them first, then to add them next. All right. So again, focus on just showing your work carefully. We have 4 to the -6, right? Because -3 times 2 is -6. If there is no exponent, it is 1, right? So we have 1 minus 2. Actually, I'll just put it in the next step. I'll do all the addition in one step. And here do the addition. So even though I'm saying addition, it's adding a negative, so it appears to be subtraction. But it's not division, it's just adding a negative is the same as subtraction. So we have 4 to the -3. And we have, let's see here. That's a -2. So we have 4 to the -1. All right. And then lastly we have, of course, it's, what's it called? Division. So now we can use the other property of subtraction, right? So we finally have 4 to the negative 3. Subtract the 1. Right. Okay. So why is this wrong? Common mistake. Why is what I just wrote incorrect? You caught it? Yes? Right. So the property says, going up here, we subtract these two numbers, right? But this minus sign here doesn't count the same as this negative down here. There's a subtraction sign, and then there's also this negative sign. So it's really minus a negative, which is adding. So I do that on purpose because it is a common mistake. Many of you probably just wrote it down and said, okay, that looks good to me. That's how easy it is to make the mistake if you're not careful about it. So even though this is a review, let's not to get too complacent. Let's be very careful. All right, so we got negative 2, which of course is 1 over 4 to the positive 2, which of course is 1/16. All right, so you try 2. All right, check with each other. And there's different ways of doing these, so it's worthwhile checking with each other even if you get the right answer, because you might see someone else like did it in 2 steps and you did it in 4 steps. And with these things, the fewer steps, the better, because that means fewer opportunities for mistakes. So with so many options, you want to find the one with the fewer steps. Not only is it faster, but you're probably going to make less mistakes. Mm-hmm. That's 2, 4, 3, I believe. Yeah. 2, 4, 3. And notice how on the top on the first step, the 3 to the 0 is just 1, so you could put it, but in effect you don't really need to. Wouldn't be wrong if you did. Just depends on your style. All right, so that's the basic Algebra 1 with a little bit of Algebra 2 in there with the roots, nth roots, and whatnot, but hopefully that's somewhat familiar. If anything, as always, focus on how you're showing your work and that it's clear. So not only that you're getting the right answer, but it's easy for somebody else that doesn't know how to do this to look at your work and they'd be able to follow what you did and how you got it. Right? In other words, you're not going to say, I didn't show any work, but I got the right answer. That's okay, right? Nay. Right? Show the work, explain the thinking, as always. The next part was graphing, right? Just graphing. So we can do graph. Just good old-fashioned t-chart, no problem, right? So we can just plug in these values that are over here and plug it into the exponent, get what the output is, or the range, and then plot those. That's the basics of graphing. That always works. You can start anywhere you want. You can start with 0, because anything to the 0 power is just 1, right? And then anything to the 1 power will just be 1/3 to the 1 would just be 1/3. 1/3 to the second would be 1/3 times 1/3, which is 1/9. So we're graphing very small numbers, fractions. And now we got to do negative powers, right? Now negative powers, another way of looking at this, a negative power, right, is that could be considered a reciprocal to the positive power. So if you know the positive power, the negative power of the same number is the reciprocal, right? So if we already have what it is to the positive 1, well, to the negative 1 is the reciprocal of that. It will be 3 over 1, or just 3. Same thing with we know the positive 2, right? The negative 2 would be the reciprocal. And by the way, it would have been the same if we reversed it. If we found to the negative first power and the negative second power first, we could have figured out it's the reciprocal for the positive 1 and the positive 2, and got 1/3 and 1/9. So all these little properties that you guys spent days going over, these are just a lot of little things that helps out, right? Now, you want to use, depending on your teacher, right, and how deep you went into graphing, the idea is that you always want to use as much of the graph space as possible. I bring that up because the default for most people is to say, let's just count every square 1, right? But if you do that here, like we're going from just to positive 2. So I'd go here to here for positive 1, positive 2, and negative 1. I'd only be using this tiny little part of the graph where I got all this other space that's just going to sit there unused. So when possible, you want to use the entire space here for your domain, which is the x, by the way, if you recall that. And since I'm only going up to positive 2 and negative 2 down to negative 2, I could probably count like, you know, maybe like this would be positive 1, this would be positive 2. That's still using only half the graph. I could use, like, if I wanted to really stretch it out, I could make count every 4 squares, right? And then I'm using the full graph. And it's a judgment call, right? But you want to err on the side of using the full graph, not squeezing it into some small, tiny thing. Because the idea is that you could probably see features of the graph if it's kind of spread out, as opposed to if it's all just condensed in a little tiny area. There's things you might not be able to realize, right? So same thing with the range. You want to look at that. That's the what goes on the y-axis. So you see we're going from what? Basically 0, 1/9 is very close to 0, all the way up to positive 9. I want to count this. I got 1, 2, 3, 4, 5, 6, 7, 8. It only goes up to 8. So you are not allowed to say, well, I just need 9. I'm just going to make it myself. No, no, no. That means we have to scale our y value. We have to scale our range as well. So you could count by 2s. You could count by even 1.5 if you wanted to, just to get there. Right? You could say this is 1.5, right? And this one would be 3. This would be 7.5, right? That way this would be 9. Like, there's different ways of doing things. So just keep that in mind. If you just counted by 2s and went 2, 4, 6, 8, 10, you could do that as well. But you don't want to go off the graph is the main thing, okay? That only goes to 7, doesn't it? We need to get to 9. So we have to count by 2s. Yeah. Let's go 2, 4, 6, 8. Now that goes up to, so yeah, we have to play with that. Let's see here. So maybe just do every square is 1.5. So 1.5. This would be 3. And then this would be 4.5, and this would be 6. This would be 7.5, and that would be 9. Right, and that'd take us to the. Like I said, it's up to you, but just don't go off the graph. Right, scale it different ways. Finally, now we have to estimate 1/9 and 1/3. Those are just very small numbers. They basically look the same on the graph, right? So we're going to do 2, 1/9, basically looks like it's on the axis. And 1, 1/3, same thing, basically looks like it's on the axis. And then when we get to 0, 1, that's going to be about right here. Because the first one is 1.5, and then when we get to -1, we go to 3. That's when it pops up to here. And then when we get to -2, we go to 9. That's when it's up here. A nice smooth curve that connects all of them. These are continuous graphs, so they keep on going in both directions. Put those arrows on there. There we go. Just for fun, just for kicks here, let's say you didn't remember anything about graphing. What could you do? There's some people that say, well, I don't remember, so I didn't do it. Don't ever be that person. There's other people that say, well, there's ways of graphing, that, I've learned in the past. How would I have graphed this in the past? And a lot of people would say your first stop for graphing would be Desmos. Right? So if you can't remember something graphing, you can always pop over here and just was it 1/3? Yeah, 1/3 to the x. Shift 6 to the x power. Right? And then you could see what it looked like. You could always go over here and change what you're counting by so you can match, oh, I only want to go like we did from -2 to +2. We counted by quarters. Same thing here. We went to maybe -3, +9, right? And we counted by what, 1.5? That's what the step. That's what I want to put those at. That way it will resemble what you're actually trying to do. Right? It'll have the same type of scale and everything on there. Also, if you don't remember this, when you're using Desmos, if you need a table, you could just put your cursor on the equation you want, hit the little edit list, and you'll see there's a little table here. And there's the exact same thing we got over on our thing here. So, you got your tools. Remember, you come across anything graphing. If you don't remember, don't just say, well, I can't remember. Well, that's fine if you don't remember. What's fine, not fine is saying, so I'm just not going to. All right, so try number 3 if you haven't already. Just plot that out. These are already numbered for you, so they're unlike the first example where you had to scale everything carefully. But just wanted to review that scaling part. That's probably the one thing that everybody could practice on for sure, is using the whole graph. And the one thing I'd say on this one is that careful how fast you jump your graph up. So you wouldn't want to do something like this, because we're only going up to +2. You wouldn't want to do something like this, right? Because at 3, if you keep on going, that should be going through 8. So 8's not even here. 8 would be way up here. So you don't want to be crossing this yet, right? So be cognizant of, well, the next value would be off the graph. So as soon as I hit here, it should be going like this, almost vertical, right? Because it's going to hit 8 somewhere, not till you get up here. So that would be the most accurate way you could draw that. Even though it's not on the graph, we'll pretend that it's, eventually would reach it. Okay, so good review for graphing. So we got our general rules up here that we're practicing. We got our graphing that we did. Right? After a while, you can do your transformational graphing, using, once you know what the parent function looks like, but we'll get to that a little later. The last property was the basic solving of equations, okay? So if you have an equation that has a variable exponent, one of the most basic ways to solve it, if it's possible, it doesn't occur a lot often, is to write the other side as the same base. So can you rewrite 8 as 2 to some power, right? So you leave the left side alone, the one that has the exponent maybe, or maybe both of them you have to change. But the other side, you try to make these the same base. So you could rewrite 8 as 2 to the 3rd. And the property of equality says if the bases are the same or equal, then their exponents are equal. If and only if, right? Those are equal. which means if I have this 2 to this power and 2 to this power, I have my solution, x equals 3, coming from the exponents. Okay? If the bases are the same. The bases have to be the same. Now obviously, what if this was 9? Well, you could write it as 3 squared, but it's not the same base, and this whole process doesn't work. And we'll work on solving those equations when they're not the same base. That's where logarithms come in. So this is the only non-logarithm method for solving exponential equations, is when you can rewrite them as the same base. Otherwise, we have to use a whole different process. But it is quite fast if you recognize it, right? Which is good to use this, because maybe you can do that. Okay? So let me pass out your assignment, let you take a look at it, and maybe we'll go over a few